And during the break, I facetiously changed the title to Talk 3.5. So that's the end of Piaget theory, at least very explicitly. I think there might be a slide with the Piaget towards the end. But I'm going to talk about teaching practice. If you don't necessarily see the connection right now, I think there is. Maybe it's my imagination. That won't matter too much. Okay, right. And if you like, frankly, I didn't have time to do a very nice set of slides. So I have copy and pasted portions out of a paper I wrote and published in 2020 on the cognitive development of the novice programmer, which you can find at that URL if you find this stuff interesting. So my apologies for the very heavy text-based next few slides, but I'm sorry, but I just ran out of time and couldn't do better. Okay, well, before I get to my own pages, I just want to mention something called mastery learning. What I'm going to be talking about is a little bit like mastery learning, but I'm not going to say much more than that about it. You can watch I recommend a very nice TED talk by Sal Khan. The URL's there. If you don't recognize Sal Khan, you've probably heard of Khan Academy. He is Khan Academy. And he gave a talk at TED called Let's Teach for Mastery. And what he was saying was, very pithily in a lovely polished 10-minute talk, so, a more general case of what I've been saying in the case of programmers. In the case of programmers, I'm saying that we just don't teach the basics very well. The students then move on to higher level tasks and they fail at them because they don't know the basics. And the analogy that Sal Khan uses in this video is, imagine if we built houses that way, where we pour the concrete for the foundations and somebody come in and inspect it and say, well, that's a pass. It's not great. It's not a great set of foundations, but I'll give you a pass. And then you build the first floor, and then you start putting the second floor on the house, and everything falls down. And people say, well, the builders couldn't build the second floor right. Well, no, the problem was that the foundations weren't right to begin with, and that's why the whole thing fell down. It's a nice talk. I recommend it. I'm going to illustrate one thing I do to take a lot of it might not be obvious from this presentation, but I believe one of the reasons why this works is it takes a lot of the abstraction out of arrays early and allows the students to see them in a much more concrete way. So I actually introduced arrays in week 2. We did until my retirement. And here's an example in Java if you can't read Java, don't worry about it, but it's just initializing an array which has 2 elements, 5 and 7, and in the next line I assign a new value to the first position, A0. And then we talk about what that means. Students have done a very similar set of tracing problems in week 1, where we don't do it with arrays, we do it with scalar variables, just integer values. So this is not a strange absolutely strange thing to be doing, but we get to start talking about arrays. The crucial thing, of course, is that in this example, I've used a constant subscript. And in week 2, I only use array scripts that are constant. I think one of the things we do is we move to using variable subscripts almost instantaneously in teaching arrays. This is giving you a preview of where we're heading. And, if I had here not A0, but AI, where I is some integer variable, that's quite an abstraction for a novice programmer to think about. The ith position of the array, it's a very general idea. They need something more concrete, or many students need something more concrete early on. And here's an example of a piece of code we kind of go through where I have arrays in weeks 2 and 3. Down here, this piece of code shifts elements of the array one place to the left. And you see it's all hard coded. We store, and we're going to wrap around the leftmost position. So we store the value from A0 for the 0th position in a nice safe place, and then we shuffle all the others across, and then we take our temporary value and put it in the right-hand end. And I showed people, by the way, I should have put this here. We trace that to understand that, and then having traced it, I will set a little example problem for students to work on. Okay, now you know how to do it to the left. See if you can write it so that it goes to the right. A lot of students can't. But that's not the issue. I mean, we're just letting some of the better students exercise themselves by giving that a generalization. But I showed them a few examples like that. Bottom line is they all have constants. And I'll give you a little preview. Well, actually, I don't say this explicitly later on, so this is probably a point worth making. One of the standard problems that novice programmers have is remembering that sometimes the code is talking about a position a value in a certain position, and sometimes the variable's referring to the position itself. And I'm sure you've seen many students with their code where they confuse those two things, a position in the array and the contents of that position. Now, when you use constant subscripts, I find there's no real confusion. That goes away. And we introduce students to the concept of an array in a way that doesn't lead to that confusion. A couple of weeks after they've done that, they then are introduced to one of their first classes in Java, and this class is what I call a list of four. It maintains a list of four numbers. I haven't shown you here the private data member which does that, but it's just an array called list which takes four integers. And okay, it returns a number of times the value in val. So we're searching through this thing called val. We're searching for the value in val occurs in the 4-element array. We're counting how many times it occurs. Val contains the value to be counted. Good. So there's the header, and here's the code when we're using constant subscripts. We're going to have a variable called count, which is set to 0, and then we have 4 if statements. So if the 0th position is equal to contains the value or is equal to val, increment the count variable. And equally, do the same thing for position 1, do the same thing for position 2, do the same thing for position 3, and then return the value. So constant subscripts is the first version. That's why it has to be list of 4, not list of n. And 4 is convenient. 4 is not too large that they can't sort of, do this. Furthermore, when it's introduced, there's always a little trace table. So when we first introduced this, we trace the code. I haven't shown you, what values are actually in list and what values in val, but that could be understood. And so, we do talk about having the students trace this sort of code so that they understand it by tracing it. Right. I'm glossing over a lot of things, but then here's the clincher. So we've gone through this one. This was my example of count element, and that's one method, one of 13 that's inside this class called list of 4. So count element is one of them. It's listed here. That was the one we did on the previous slide. And then there's the start of them. I sat down one day and I tried to come up with as many simple things that we could do on a list of 4 integers as I could come up with. We can copy it into another list. We can find a value when the values are unsorted. We can put a new value in the first position, put a new value in the last position, look for the smallest value, and so on, blah, 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 blah. And I even have a 2-string method. Okay, I'm not going to show you the code for all 13. That would be pretty mind-blowing, but give the students the code for these. This is not like I show them this one and then I say, now go away and write 12 other pieces of code like it. I give them this code, and we do. I may not necessarily discuss in lectures all 13, but I do provide written materials and even some recorded videos sometimes for all 13 methods, and I trace all 13 as I introduce them to the students. Right, and about 2 weeks after they have that lecture, they go into a lab and they must correctly implement all 13 methods. So code of this type for count element and similar code for the other 12, all using constant subscripts because that's all they know at this stage. And here's the clincher. It must work. They must get all 13 right. It's an automatic submission system. They find out immediately whether they got it right or wrong. So they walk out of the lab knowing whether they got it right or wrong. And it's not such a big drama if they don't get it right, because this is about like week 5 of the semester. Okay, you got it wrong this week. Don't worry. Come back and do it next week. And you can have as many attempts as you need to get this right. Now, there is a cost to having to come back next week, which is there's now a lab test every week, and eventually you must pass all of them by the end of semester. So you're starting to sort of compress the amount of time you've got to do all the tests, but that's okay. It's not a disaster. Just come back next week, study some more between now and then, and try again. So yeah. Then what happens? Second version of list of 4. We've done that one with the constant subscripts, and now I introduce a new version. I won't show you the header and so on. Now we have a variable called I, so that now instead of 0, 1, 2, 3 explicitly, now we have a variable called I, which is initialized to 0. And then after each one, we increment the value and find the return count. And of course, we have a trace table so we can see how this works. We talk about that. How do I sell this to students? It looks, I mean, you know, this is easier, isn't it? Why are we bothering with all that more complicated stuff? Well, one of the selling points I say to the students is, suppose you wanted to modify your code so that it maintained a list of 100 elements. Well, you actually don't have to change any, you don't have to write any new code. You just copy and paste this as many times as you need it. That's kind of nice. That's the justification I give the students. But I mean, the real justification is I'm introducing the concept of using a variable as a subscript. And furthermore, I'm doing it in a context where there's no loop involved. So I'm sort of breaking things up into nice manageable pieces for them. Right, and then of course, there are 13 methods, just as there was before. And by the way, when I'm showing them this, I mean, I might have sometimes in the lecture, I might have this code side by side with it as we compare the two and see how they work. And so we do that. And then, of course, that was count elements. And then there's 13 of those. Just as there was a copy list and a find unsorted insert first for the first version, there's equally versions for those. And again, I give the students all that code. I don't necessarily go through it in lectures, but there will be supporting materials for every method if they need it. And then a couple of weeks after that, so we're getting to about week 7 or 8 of semester, I can't quite remember, they walk into a lab and they have to do a lab test where they've got to implement things this way. And again, it must work. But if no dramas, if it doesn't, come back next week and try again. And then finally, I'm going to cut that short a bit. You're getting the idea now. We introduced versions of count element and the other methods, 3 and 4. Now we finally introduce the loop. You know, we say, look, I say to them, what was the initial value in 0? I say, sorry, the initial value in I, or 0. And what did we do after each assignment statement like this? We incremented it, okay. And we did it how many times? Well, we did that the number of times that we've got elements in the array. So when I write the code to still do it on 4 elements, we initialize it to 0. That's what you just told me when you looked at the version I just showed you. We increment it each time around and we have a test. We stop after the right number of times. So that's the version 3. And then version 4 is the trivial change where I replace 4 with list.length, and now it works for everything. So I've broken up introducing arrays and certain algorithms on arrays into a series of tasks that build their way up. And at each stage, I'm insisting that the students reproduce that code in a lab, and a lot of code, 13 methods. And of course, they must get it right, must correctly invent all 13 methods. And that's a taste of it. This is what's called a killer plan, by the way. I showed you the Khan Academy thing a few moments ago where he talked about mastery learning. Killer plan is kind of mastery learning, but it's slightly different. No, I won't go into why. The killer plan is nothing new. In the paper, it's reference 12, and reference 12 is for your convenience here. So it's a paper written in 1968. So it's a self-paced process. The essential element of a Keller plan is that the student needs to, that you need to understand, is that the knowledge to be learned is broken into a sequence of units, and students must pass a test on a unit before that student is allowed to move on to the next unit. And the student may attempt a test for a unit as many times as required. So I've implemented a Keller plan. Video lectures so that it's self-paced, so on. Now, this didn't occur to me until I'd done it, but it now seems so obvious. I'm astonished I never figured this out. In Australia, we're heading into flu season, as you probably are in South Africa. This line's showing you the frequency of flu in Australia, assuming that this year's flu season is a normal season. It may not be because of COVID. This is a diagram from before COVID. So around about the time, I don't know exactly when your semesters start, but around about the time when our second semester, our spring semester starts here in Australia, flu season is really starting big time and continues, is running pretty rampant mid-semester and is running all the way through semester. And unsurprisingly, there are students who miss classes because they're too sick. And it never occurred to me until I did this. I only found this out when I started talking to students. There were students who were missing 1 or 2 weeks, and they'd come back and they'd catch up. They'd talk to me about how they were able to catch up because of the nature of this Keller plan. And it occurred to me that for years I've been teaching students, and a percentage of them had probably been failing just because I'd missed a couple of weeks because of illness. But before we started making videos and all these other things, the relentless pace of lectures meant that if you missed 2 weeks of lectures because of illness, you probably weren't going to catch up. Mundane, but I was just astonished at how I'd never figured this out, frankly. Now, one of the things you'll be worrying about, I mean, I give them the code for all 13 is given to the students. Then I insist they must make it work. Am I boring the students to hell? I mean, surely the students want to be creative Picassos, don't they? Well, yes, some of them do. By the way, what I'm talking about here is what you do to get a bare minimum pass in the subject. I'm not talking about what the Picassos and the watercolorists do. They do quite normal sorts of activities to assignments and so on. But am I boring the students by making them all do this? Apparently not. This is the one key. There are about 10 questions on our end of the semester survey, but I can tell you that the university management only care about this one. Overall, I'm satisfied with the quality of this subject. And you'll find here that for this subject, the way I'm teaching it with the Keller plan, 59% of students agreed, strongly agreed, and 25% of the students agreed that they were satisfied for a combination of 84%. Now, I don't know what it's like in South Africa, but first semester programming subjects at most Australian universities do not get an 84% positive record out of the students. So they're pretty happy. As the person was saying earlier who asked a question, a lot of the unhappiness that a lot of students have is because we ask them for assignments to write large programs and they can't do it. I mean, what could make you more unhappy and less motivated to study programming than being presented with a task to write a program and you don't have the skills to do it? Here I'm giving a student something they can do. Now, but it still might be setting off alarm bells, and that's fair enough, because on this quick introduction that I'm giving you, this sounds an awful lot like rote learning. I'm giving the student codes, various methods, and then I'm asking them to reproduce it in the labs. And yesterday, the legitimate concern is that the students won't generalize from the code. Now, let me back up for a second and say, try to say pithily, I am trying to get them to generalize because I'm giving them not one method, I'm giving them 13. And what I'm trying to do in my teaching is to get them to see what's similar across all the methods. So in that sense, I'm trying to generate it. But I agree that it's not obvious that it's going to work. Now, yesterday, Roxanne talked about the problems of having students memorize code. If Roxanne is listening, by the way, don't worry, Roxanne, I'm not about to diss you. I was very happy with everything you said yesterday. No problem. But I just want to make a connection in this way that yesterday Roxanne said that there were real concerns about giving students lots of code and asking them to memorize it, whether they'd be able to generalize to new cases and so on. Absolutely legitimate concern about what I've described so far. But all I'll say is that every method of teaching can be done badly. And as Roxanne was sort of saying, it is possible for a teacher to do pair programming badly. And she offered up some very nice techniques to stop that from being a bad process. Equally, what I'm suggesting to you here, where students are given code and they have to reproduce it in a Keller plan, that can be done badly, and it can result in students doing all sorts of bad behaviors like trying to rote learn the code. It can be if you do it wrong. You have to work at making it right. I can't give you a long version of how I try to make it right. And I'll say in a sense, this is where the education research stops and the art of teaching begins. I have never suggested that all teaching can be reduced to research level questions. There's still a lot of art in my teaching, and there always will be. Well, if I ever teach again, there always will be. So let me try and hint at the good things you can do. Well, the pre-tracing student can't do these things, so let's not talk about them. You've got to sit down with those students and get them to trace code and get them to improve their tracing before they can productively learn the pieces of code I'm giving them. Now, the students who can post-trace, they're not a problem either. The interesting students are the tracing stage students, the students who can only trace but don't see the abstractions. Those students, if left to themselves in a bad teaching environment, will attempt to rote learn the code. And we've got to stop them from doing that. Well, try to stop them from doing it. As I like to say to people, you can lead a horse to water, but you can't make it drink. And you can lead a student to learning, but you can't make them think. In the end, you can do all sorts of good things, but in the end, the student's got to make a decision they want to learn something. So So we've got to stop that happening, the rote learning, and we've got to have conversations, teaching interventions with students that stop them from thinking about this as a rote learning exercise. So I have all sorts of teaching moments with the students where, oh, hang on. Our task as a teacher is to lift the student from this tracing level way of approaching the questions to a post-tracing level where they see the abstraction. And as I've written down the bottom here, a mantra that I say so often during semester, the students start teasing me with it by the end. I keep saying to them, remember the pictures, not the code. Before you go to the lab test, you should have a strong mental image of how the algorithm works. And then from that, you work out the code. You don't memorize the code. But to the stubborn student who doesn't buy that, the tracing student who may attempt to rote learn it, I have teaching moments like this, particularly when they've made their first attempt at the lab test and they've failed. Well, let's say, no, before they get to lab test, I've said, okay, you've rote learnt one method. Congratulations. Are you really going to rote learn 12 more? Because the trouble with rote learning in this situation is rote learning one method doesn't do anything to help you rote learn the other methods, the other 12 methods. When you rote learn, everything's a special case. So, and then the other one is, which is more productive when a student has failed the first lab test, I say to them, look, you didn't get it to work. What are you going to do? Well, halfway through the lab test is when I often will have this discussion. It's not working. Okay, you couldn't remember it right. Okay, what are you going to do now? Random permutation? And one of my little spiels there is, well, random permutation can work pretty well. After all, 4 billion years of evolution produced us, but it did take 4 billion years. All right. You don't have 4 billion years to get your code working. Let's have these sort of conversations with students to try and bring their thinking around to the right way. And finally, I think this is just about the last slide. And I sort of complete the circle in a way with this slide. I was very happy when I realized I could write this. Yeah, I'm saying to the students, I said here at the bottom, remember the pictures, not the code. So much do I say it in class that the students start teasing me about it. I start to say it and they finish it for me. And I'm thinking to myself, now I put on my researcher hat and say, well, I should evaluate this sort of thing in my exam. And this could be a 5th trip around the research cycle. If I did it, chances are I won't because I'm enjoying retirement too much. But it could have been the 5th trip around the circle if I hadn't retired. And for that matter, maybe you can do the trip for me and tell me what happened. Tell me about the sights you see as you make the trip. So here's the idea. If we really want students to remember the pictures, not the code, how about this then as an exam question? And therefore as a research study. Here's the question. Here is some code we studied in lectures. You could also give them a piece of unseen code, but let's start with the idea that they've seen the code already. This code, and then we tell them what it does. I don't know, it counts the number of elements of the array, it sorts the array, I don't know. Then we give them the code. We give them the code. We're sort of inverting the process. Usually we tell students what we want them to write and they write it. Here I'm saying, give them the code and then say, waiting for my image to come up. Come on, here it is. Coming up. PowerPoint's letting me down at just the crucial moment. Then the question is, using words and possibly diagrams, explain how this code achieves what it does. Probably an application level question, by the way, Bloom level application, I think. Analysis, Bloom level. Using words and possibly diagrams, explain how this code achieves what it does. So I was asserting in the last few slides that what I wanted to do in the teaching by giving students lots of code was to get them to abstract and start to see the pictures, start to look beyond the code. Well, really, I should test for that in the exam. And it would be a good way of finding out whether it's working and how I should improve things, if I should drop this idea or try it and modify it in some way for the following semester. So I should be putting, or if I'd been still teaching, I should have been putting questions like this in my exam to find out. But I do look forward to reading your research paper when you do ask questions like this. I hope somebody out there will try it. And I think that is, well, the end of talk 4. There you go. That's it. Thank you very much. I'm going to back up and leave that there just for a second. I've finished and we still have a little bit of time. So organisers, please, yes. What would you like to do?
Questions, Prof. The first question is this approach that you used, is it the objects first approach? That means you first introduce objects before you introduce the rest, or other way around?
Yeah, good question. Our approach is, what some people call objects light. That's a curriculum decision made by the university. But I'll say, so we do introduce objects, classes and objects. And this is a class. It's implemented as a class, where the thing that lives inside the class is a list of 4 elements, and then these are the various methods that work on it. So in that sense, it is OO, very, very light OO, but it is OO. It's done in an OO context, but it is very much, it remains, our focus is really on the methods inside the object. So in some sense, you could say we are procedurally, not exactly still heavy, but we're heavier on procedural than we are on objects. Would I do the same thing for objects? I'd have to sit down and think about whether it works. It would work for an objects heavy kind of approach. So I don't know is the short answer, I guess.
Yes, thanks. That's the answer. And then there's a question. Where would they get this 13 methods you referred to?
Where would they get them from? I give them to them.
You send us an email.
I'm sorry? Oh, would I give you that? Is that the question?
Yes. Yes.
Okay, I'll be very happy to. If I don't think to do it myself, please remind me to do so. I'll be very happy to share all this. In fact, I used to give it to the students as a hard copy handout in week 1. It has all the code for all the methods, all in hard copy. And I called it the subject is called Programming Fundamentals, so I called it the Programming Fundamentals Coloring In book. And maybe I'll send you that because it does. Well, we'll see. I'll figure out something, but I'll be very happy to share any of these things with anybody.
Thank you very much, because I really think that people enjoyed it so much what you said, and it is really a good approach. I can see it's a very, very good approach, and it can really help. So it is important that we look at all these things when we introduce the changes in the programming in future in our university. And I think a lot of the teachers and the Department of Education is also going to look into that to do it in future. I don't see any other questions that we've got now. We say thank you very, very much to Prof. Lister. We really, really enjoyed what you've learned to us, what we've picked up from you. And with this, we must say, like you see, with all the hand clapping and the thumbs up, everybody really, really enjoyed your presentations. And we look forward to working with you again and bringing you out to South Africa, that we can have another webinar series in future in South Africa. I really think it will contribute a lot to the research in South Africa and working together with you in future research in this environment. I think you triggered a lot of the people that never thought about this research. You triggered them to really do research in this environment and see how we can make it much better for our students. We really appreciate it, and we say thank you very, very much. And I ask everybody to clap our hands for Prof.
Thank you very much. That's kind of you. Thank you to all of you. I think, as I may have said before, I spent most of some of you were in the same situation as me. I spent much of my career in environments where teaching was a secondary thought for most academics, and sometimes I got a bit lonely and frustrating in that environment. So it's always a pleasure to meet people like you and to chat about this stuff. So thank you.